We've been told nothing moves faster than light. But what if gravity didn't care? What if it could reach across the cosmos instantly, connecting stars, galaxies, even minds, in ways we can't yet explain? For over a century, physicists have insisted that nothing can break the cosmic speed limit. Light races through space at exactly 299,792,458 meters per second. Every force, every signal, every piece of information must respect this boundary. It's not just a suggestion from nature. It's an absolute law carved into the fabric of reality itself. But gravity has always been different, strange, mysterious in ways that make even the most brilliant scientists pause and wonder. When Isaac Newton first described it 300 years ago, he imagined it as instantaneous. A star dies in a distant galaxy, and its gravitational influence vanishes everywhere at once. No delay, no waiting, just immediate, universal response. Einstein changed everything when he showed us that gravity isn't really a force at all. It's the curvature of space-time itself, rippling outward like waves on a cosmic pond. These ripples, he said, must travel at exactly the speed of light. No faster, no exceptions. Yet something feels unsettling about this picture. When you drop an apple, it falls toward Earth, as if the planet's gravity knows exactly where the apple is, right now, not where it was 8 milliseconds ago when light last left its surface. When the moon orbits our planet, it moves as if Earth's gravitational field responds instantly to its position. Could there be something we're missing? Could gravity be the one thing in the universe that ignores the speed limit completely? And if it does, what would that mean for everything we think we know about space, time, and the fundamental nature of reality? To find out, we have to revisit how we first thought gravity worked. We need to go back to a time when instant action across infinite distances didn't seem impossible, but inevitable. Back to Newton's universe, where gravity was a force that knew no delay and respected no boundaries. Picture London in 1687. The Great Fire has been rebuilt from ashes. Coffee houses buzz with intellectual debate, and in a cramped study filled with alchemical equipment and mathematical papers, Isaac Newton puts the finishing touches on what will become the most influential book in the history of science. He calls it Philosophiae Naturalis, Principia Mathematica. We simply call it the Principia. Newton had been wrestling with a cosmic puzzle. Why do planets orbit the sun in perfect ellipses? Why does the moon circle Earth without flying off into space? Why does an apple fall straight down instead of drifting sideways? The answer, he realized, was a single, universal force that reaches across all of space and touches everything with mass. But Newton's gravity was unlike anything anyone had imagined before. It didn't need to travel. It didn't need time to cross the vast distances between celestial bodies. In Newton's universe, when Jupiter shifted its position even slightly, the sun felt that change instantly. Not after 43 minutes when light from Jupiter would reach the sun. Not after gravitational signals propagated across 800 million kilometers of space, instantly. This wasn't an oversight or a simplification. Newton genuinely believed that gravitational force acted across space without any delay whatsoever. When he wrote his famous inverse square law, he was describing a force that could reach from one end of the universe to the other in 0 time. The mathematics was elegant and precise. Every object with mass attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. But there was something deeper and more radical hiding in Newton's equations. His law implied that information itself could travel instantly. If the sun suddenly vanished, Earth wouldn't continue orbiting for another 8 minutes until the darkness arrived. According to Newton, our planet would immediately fly off into space, somehow knowing that the sun's gravitational influence had disappeared. This concept of action at a distance troubled many of Newton's contemporaries. How could the Sun reach across 93 million miles of empty space and pull on Earth without anything connecting them? Newton himself admitted he found it philosophically unsatisfying. In a letter to Richard Bentley, he wrote that the idea of one body acting upon another through empty space without mediation was so absurd that no person competent in philosophical matters could ever accept it. Yet the mathematics worked perfectly. Newton's laws predicted planetary motions with unprecedented accuracy. They explained ocean tides, the precession of equinoxes, and the paths of comets. When Edmund Halley used Newton's equations to predict that a particular comet would return in 1758, it arrived right on schedule. The universe seemed to operate exactly as if gravity truly was instantaneous. For over 2 centuries, physicists lived comfortably with this paradox. They used Newton's equations to send spacecraft to other planets, predict eclipses decades in advance, and discover new worlds by observing their gravitational effects on known objects. The instantaneous nature of gravity wasn't just convenient mathematics. It seemed to be how nature actually worked. But seeds of doubt were already growing. In 1865, James Clerk Maxwell published his equations describing electricity and magnetism. These showed that electromagnetic waves must travel at a finite speed. That speed turned out to be exactly the speed of light. Suddenly, physicists realized that at least some forces in nature couldn't act instantly. This created a troubling inconsistency. Why should gravity be special? Why should it alone among all forces be exempt from having a finite speed? Maxwell himself wondered whether gravity might also propagate as waves, perhaps at the same speed as light. But his electromagnetic theory offered no clear path to understanding gravitational propagation. The problem deepened when physicists began to understand the implications of finite signal speeds. If information cannot travel faster than light, then truly instantaneous action at a distance becomes impossible. There would always be a delay, however small, between cause and effect across any distance in space. Yet astronomical observations continue to support Newton's instant gravity. When astronomers calculated planetary orbits, they found no evidence of gravitational delays. The planets moved exactly as Newton's equations predicted, as if the Sun's gravity reached them without any travel time whatsoever. This wasn't just a minor technical detail. It struck at the heart of how we understand causality itself. In Newton's universe, events could influence other events across arbitrary distances without any delay. The gravitational field was simply there, everywhere, all at once, responding instantly to changes in the distribution of matter. Consider what this means for a simple system like Earth and Moon. As the Moon orbits our planet, it continuously changes direction, which means it's constantly accelerating. This acceleration should create ripples in the gravitational field that propagate outward at some finite speed. But Newton's theory suggests no such ripples exist. The gravitational influence is always perfectly synchronized with the Moon's actual position, never its past position. Even more remarkably, Newton's gravity implied a kind of cosmic awareness. Every particle in the universe somehow knew about every other particle, no matter how distant, and adjusted its motion accordingly without any delay. It was as if space itself was alive with invisible connections that transmitted gravitational information faster than anything else could travel. This picture of instant gravity created a universe that was fundamentally different from our everyday experience. When you push a friend, they feel it immediately because you're in direct contact. When you shout across a field, your voice takes time to travel through air. When you turn on a flashlight, the light beam races away at a finite speed. But in Newton's cosmos, gravity worked more like telepathy than like any physical process we could directly observe. The mathematical beauty of Newton's system made it easy to overlook these philosophical problems. His equations were so successful at predicting natural phenomena that most physicists simply accepted instantaneous action at a distance as a brute fact about how the universe operates. If the mathematics worked, perhaps the underlying mechanism didn't matter. But a few prescient thinkers worried about the deeper implications. If gravity could act instantly across any distance, what prevented other kinds of information from doing the same? Could there be instantaneous communication between distant civilizations? Could the past and future be connected in ways that violate our intuitive understanding of cause and effect? These questions would remain largely academic until a young patent clerk in Switzerland began thinking seriously about the nature of space, time, and the speed of light. Albert Einstein would soon show that Newton's instant gravity, however mathematically elegant, was fundamentally incompatible with the deeper structure of reality. But first, let's dive deeper into just how strange Newton's instant gravity really was. Imagine you're standing on Earth, looking up at the moon. According to Newton, the moon feels Earth's gravitational pull based on exactly where our planet is right now, at this very instant, not where Earth was 1 1/3 seconds ago when light left its surface to reach the moon, not where Earth appeared to be from the moon's perspective, accounting for the finite speed at which information can travel, but where Earth actually is, in real time, across 384,000 kilometers of space. This creates a kind of cosmic synchronicity that defies our everyday understanding of how information works. When you wave at a friend across a football field, they see your wave a tiny fraction of a second after you make it, because light takes time to travel from your hand to their eyes. When radio signals travel from Earth to Mars, they take between 4 and 24 minutes depending on the planet's positions. But Newton's gravity somehow bypassed all these delays. The implications become even more mind-bending when you consider what happens during a solar eclipse. As the moon passes between Earth and the sun, it blocks sunlight from reaching us. We see the eclipse happen in real time, right? Actually, no. We see it 8 minutes and 20 seconds after it really occurs, because that's how long sunlight takes to travel from the sun to Earth. But according to Newton's theory, Earth feels the gravitational effects of the moon's changed position relative to the sun instantly, not 8 minutes later. This means that in Newton's universe, gravity provided a kind of faster-than-light communication system. If you could somehow measure gravitational forces with perfect precision, you could detect events happening around distant stars before their light reached you. You could know that a massive star had exploded as a supernova the instant it happened, not years later when the light from the explosion finally arrived at Earth. Newton himself was deeply uncomfortable with this aspect of his theory. He called it an absurdity and spent considerable effort trying to find a mechanical explanation for how gravity might work. Perhaps space was filled with invisible particles that pushed and pulled on massive objects. Perhaps there were ethereal fluids that carried gravitational influences from one body to another. But every attempt to create a mechanical model of gravity failed to match the precision of his mathematical law. So Newton made a pragmatic choice that would influence science for centuries. He decided to describe what gravity does without worrying about how it does it. His famous phrase, "I do not feign hypotheses," reflected this approach. The mathematics worked beautifully. The predictions were accurate. The mechanism could remain a mystery. This philosophical stance had profound consequences for how scientists thought about natural laws. It suggested that the universe might operate according to principles that were fundamentally beyond human intuition. We could measure, predict, and use these principles without necessarily understanding them at a deeper level. Mathematics became more important than mechanical models. But the mystery of instantaneous action at a distance never went away. Throughout the 18th and 19th centuries, natural philosophers continued to puzzle over how Newton's gravity could work. Some proposed that space itself had special properties that allowed gravitational influences to propagate instantly. Others suggested that time might not be as absolute as everyone assumed. The most prescient thinkers began to suspect that Newton's instant gravity might be an approximation rather than exact truth. Perhaps gravitational influences really did take time to travel from one object to another, but this time was so small compared to astronomical distances that it appeared instantaneous in most situations. This suspicion grew stronger as physicists developed better understanding of other forces in nature. When scientists discovered that electric and magnetic forces propagate as waves at the speed of light, it seemed increasingly unlikely that gravity alone would be exempt from having a finite propagation speed. Yet, the observational evidence continued to support Newton's instant gravity. The most sensitive astronomical measurements of the 19th century could detect no gravitational delays. When astronomers used Newton's equations to predict the return of Halley's Comet, it arrived within hours of the predicted time after a 76-year journey around the solar system. Such precision would have been impossible if gravitational forces propagated slowly enough to accumulate significant delays. This created what historians of science call Newton's gravity paradox. The theory worked too well to be wrong, but it implied physical processes that seemed impossible according to other branches of physics. Something had to give, but it wasn't clear what. The resolution would come from an unexpected direction. Instead of trying to fix Newton's theory of gravity, Einstein would completely reimagine what gravity is. Instead of a force acting instantly across space, Einstein would show that gravity is the shape of space and time themselves. But that revolutionary insight was still decades away. For now, in the early 1900s, physicists lived with the paradox of instant gravity. They used Newton's equations every day to solve practical problems, while secretly wondering whether the universe could really be as strange as the mathematics suggested. Little did they know that the true strangeness of gravity was only beginning to be revealed. Then came Einstein and a radical rethinking of what gravity even is. In 1905, Albert Einstein was 26 years old, working 6 days a week at the Swiss Patent Office in Bern, evaluating applications for electromagnetic devices and mechanical inventions. But in his spare time, he was quietly revolutionizing our understanding of space, time, and reality itself. That year, he published 4 papers that would change physics forever. One of them introduced the world to special relativity and its most famous consequence: nothing can travel faster than the speed of light. This created an immediate problem for Newton's instant gravity. If no information could propagate faster than light, then gravitational influences couldn't possibly act instantaneously across space. There had to be a delay, however small, between a change in one massive object and its gravitational effect on distant objects. But Einstein's special relativity offered no clear alternative to Newton's gravitational theory. For the next 10 years, Einstein wrestled with this contradiction. He knew that Newton's gravity had to be wrong, but he couldn't figure out what should replace it. The breakthrough came when he realized he was asking the wrong question. Instead of asking how gravitational forces propagate through space, he began asking whether gravity was really a force at all. The key insight arrived during what Einstein later called the happiest thought of my life. He was sitting in his office at the Patent Bureau when he suddenly realized that a person falling freely under gravity feels no gravitational force whatsoever. If you're in an elevator and the cable snaps, you don't feel yourself being pulled downward by Earth's gravity. You feel weightless, floating freely as you and the elevator fall together. This simple observation led Einstein to a radical conclusion. What we call gravity isn't actually a force pulling objects toward massive bodies. Instead, massive objects curve the fabric of space-time itself, and objects simply follow the straightest possible paths through this curved geometry. It's not that Earth pulls the moon toward it. Rather, Earth's mass warps space-time in such a way that the moon's natural, straight-line motion through 4-dimensional space-time manifests as an orbit in our three-dimensional space. Einstein spent years working out the mathematical details of this insight. The equations were fiendishly complex, involving advanced geometry and tensor calculus that few physicists of his era understood. When he finally published his general theory of relativity in 1915, it represented one of the most profound conceptual revolutions in the history of science. In Einstein's new picture, space-time itself becomes dynamic. It can stretch, compress, ripple, and curve in response to the matter and energy it contains. Massive objects create wells and valleys in the space-time fabric, while less massive objects follow geodesics through this curved geometry. What looks like gravitational attraction is really just objects taking the path of least resistance through warped space-time. This geometric interpretation of gravity immediately resolved the paradox of instantaneous action at a distance. In Einstein's theory, there is no gravitational force propagating from one object to another. Instead, each massive object curves the space-time in its immediate vicinity, and this curvature extends outward at exactly the speed of light. Objects respond to the local curvature of space-time right where they are, not to the distant objects that created that curvature. But Einstein's revolution went far deeper than just resolving Newton's paradox. It predicted entirely new phenomena that had never been observed before. Light rays should bend when passing near massive objects, following the curved geometry of space-time. Clocks should run slower in stronger gravitational fields, because time itself is part of the fabric that gets warped by mass and energy. And most remarkably, accelerating masses should create ripples in space-time itself, ripples that propagate outward at the speed of light, carrying energy away from their source. These gravitational waves were perhaps the most astonishing prediction of Einstein's theory. When massive objects accelerate, particularly when they orbit each other at high speeds, they should create disturbances in space-time that spread outward like ripples on a pond. These waves would compress and stretch space itself as they passed, but the effect would be incredibly tiny, far too small to detect with any technology available in Einstein's time. The mathematical elegance of general relativity was breathtaking. Einstein's field equations related the curvature of space-time at any point to the density of matter and energy at that same point. The equations were local, meaning that what happens at any location depends only on conditions in the immediate neighborhood, not on distant objects acting across empty space. This locality principle eliminated the troubling action at a distance that had plagued Newton's theory. Yet Einstein's equations also preserved all the successful predictions of Newton's gravity, at least in the limit of weak gravitational fields and slow motions. This was crucial because Newton's theory had been tested countless times over 2 centuries and found to be extremely accurate for most practical purposes. Einstein's theory had to reduce to Newton's in the appropriate circumstances, while also making new predictions that could be tested. The first dramatic confirmation came during a solar eclipse in 1919. Arthur Eddington led expeditions to observe how light from distant stars was deflected as it passed near the sun. Einstein's theory predicted that starlight should be bent by exactly twice the amount that Newton's theory would suggest if you naively applied Newton's formulas to light rays. When Eddington's measurements confirmed Einstein's prediction, it made headlines around the world and transformed Einstein from an obscure physicist into a global celebrity. But the real power of Einstein's geometric interpretation emerged when physicists began exploring its consequences for extreme situations. What happens near objects so massive and dense that they create deep wells in spacetime? What occurs when spacetime curvature becomes so severe that it closes in on itself? Einstein's equations suggested the existence of objects so gravitationally powerful that nothing, not even light, could escape from their vicinity. We now call these objects black holes. The equations also predicted that the universe itself might be expanding or contracting, with space-time itself growing larger or smaller over cosmic time. This seemed so strange to Einstein that he initially modified his equations to prevent such behavior, introducing what he called a cosmological constant. Later, when observations confirmed that the universe really is expanding, Einstein called this modification his greatest mistake. Perhaps most importantly for our story, Einstein's theory made specific predictions about how changes in gravitational fields should propagate. When massive objects accelerate, they create gravitational waves that travel outward at exactly the speed of light. This meant that gravity, like all other fundamental interactions, respects the cosmic speed limit. There can be no instantaneous action at a distance in Einstein's universe. Consider what happens when a massive star suddenly collapses to form a black hole. In Newton's theory, objects throughout the galaxy would instantly feel the change in gravitational field as the star's matter becomes compressed into a tiny region. But in Einstein's theory, the news of the collapse travels outward as gravitational waves at the speed of light. Objects at different distances feel the change at different times, with more distant objects experiencing the effects later. This seemingly abstract difference has profound implications for how we understand causality. In Einstein's universe, causes always precede effects, and information about events propagates outward from their source at a finite speed. The future cannot influence the past, and distant events cannot have instantaneous effects on local phenomena. The universe has a rational causal structure that protects the logical flow of time. Yet Einstein's theory also revealed that space-time itself is far stranger and more flexible than anyone had imagined. Space and time are not fixed backdrops against which events unfold, but dynamic participants in the cosmic drama. They can be stretched, compressed, twisted, and curved by matter and energy. Time can slow down or speed up depending on gravitational conditions. Space can expand, contract, or even fold back on itself in exotic configurations. This flexibility of space-time raised new questions about the nature of gravitational propagation. While changes in gravitational fields propagate as waves at the speed of light, the underlying space-time geometry can have complex, non-local properties. Distant regions of space can be connected through wormholes or other topological features that might allow for exotic forms of communication or travel. Einstein himself was deeply uncomfortable with some implications of his theory. He famously opposed the quantum mechanical interpretation of reality, arguing that God does not play dice with the universe. But his geometric theory of gravity would eventually merge with quantum mechanics to create even stranger possibilities, including the prospect that space-time itself might emerge from more fundamental quantum processes. The transition from Newton's instant gravity to Einstein's curved space-time represents one of the most dramatic paradigm shifts in the history of science. Instead of a mysterious force acting instantly across empty space, gravity became the manifestation of space-time geometry itself. Instead of absolute space and time, serving as fixed stages for physical events, space-time became a dynamic participant that could be shaped by matter and energy. But even Einstein's revolutionary theory left important questions unanswered. If gravitational waves travel at the speed of light, why do planets seem to orbit as if gravity acts instantaneously? How can we reconcile the apparent immediacy of gravitational effects with the finite speed of gravitational wave propagation? And could there be circumstances under which even Einstein's speed limit might be violated? Then came the question that would haunt physicists for decades. If gravity truly travels at sea, can anything violate that rule? The speed of light isn't just fast, it's the cosmic speed limit, the ultimate barrier that separates the possible from the impossible. At 299,792,4 458 meters per second. It represents the maximum rate at which any cause can produce an effect, any signal can carry information, any influence can propagate through space. Einstein's special relativity doesn't just suggest this limit exists. It proves that violating it would tear apart the logical structure of reality itself. But what if something could break this rule? What if there were phenomena in nature that simply ignored Einstein's speed limit and acted instantaneously across any distance? The implications would be so profound that they would force us to completely reconsider everything we think we know about space, time, and causality. To understand why faster-than-light travel seems impossible, we need to dive into the heart of Einstein's special relativity. The theory rests on two simple postulates. First, the laws of physics are the same in all reference frames moving at constant velocity relative to each other. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. These innocent-sounding assumptions lead to extraordinary consequences. As objects approach the speed of light, strange things begin to happen. Time dilates, meaning that clocks run slower from the perspective of stationary observers. Lengths contract, with objects becoming shorter in the direction of motion. And most importantly for our story, the mass of moving objects appears to increase without limit as their velocity approaches the speed of light. This last effect creates an insurmountable barrier. To accelerate any object with mass to the speed of light would require infinite energy. It's not just practically impossible, it's theoretically forbidden by the structure of space-time itself. Only massless particles like photons can travel at the speed of light, and they must always travel at exactly that speed, never faster or slower. But what about information? Could there be ways to send signals faster than light, even if we can't accelerate massive objects to such speeds? This question becomes crucial when we consider gravity, because gravitational effects seem to convey information about the positions and motions of distant masses. Einstein's special relativity reveals why faster-than-light signaling would be catastrophic for causality. The theory shows us that the concept of simultaneity is relative. Events that appear simultaneous to one observer may occur at different times for another observer, moving at a different velocity. This relativity of simultaneity means that if information could travel faster than light, it would be possible to send messages into the past. Imagine you're on a spaceship traveling at 90% the speed of light, and you send a faster-than-light signal to a friend on Earth. From your perspective, the signal travels forward in time and reaches your friend after you send it. But from the perspective of observers on Earth, the relative motion between you and them means that your signal actually arrives before you sent it. Your friend could then send a faster-than-light reply that reaches you before you originally transmitted your message. This creates what physicists call a causal paradox or grandfather paradox. You could potentially receive information about future events, use that knowledge to change your actions, and prevent those future events from occurring. The logical contradictions multiply rapidly. If effects can precede their causes, then the rational structure of time breaks down entirely. The mathematics of special relativity makes this breakdown precise and unavoidable. Any object or signal that travels faster than light in one reference frame will travel backward in time in some other reference frame. There's no way around this conclusion if Einstein's postulates are correct. Faster-than-light travel and time travel are mathematically equivalent, and both lead to logical paradoxes that seem to render them impossible. Yet nature has always been full of surprises. Throughout the 20th century, physicists discovered phenomena that seemed to challenge the absolute nature of the light-speed barrier. Some of these turned out to be misunderstandings or misinterpretations. Others revealed subtle aspects of relativity that most people don't appreciate. But a few pointed toward genuinely mysterious features of reality that we still don't fully understand. One of the most famous challenges to the speed limit came from theoretical particles called tachyons. These hypothetical objects would have the strange property of always traveling faster than light, just as normal particles always travel slower than light. Tachyons would have imaginary mass, meaning their mass squared would be negative, which sounds absurd but isn't necessarily impossible mathematically. If tachyons existed, they would create a bizarre mirror world where faster motion requires less energy rather than more. A tachyon slowing down would actually gain energy, while a tachyon speeding up would lose energy. At infinite speed, a tachyon would have zero energy. The physics would be completely backwards compared to our everyday experience. More troubling, tachyons would allow the construction of devices that could send information into the past. By carefully arranging transmitters and receivers on spacecraft moving at different velocities, you could create closed, time-like curves that would permit communication with your own past. The grandfather paradox would become a practical engineering problem rather than a philosophical thought experiment. Despite decades of searching, no one has ever found convincing evidence for tachyons. They remain purely hypothetical, mathematical curiosities that illustrate the strange boundaries of possible physics. Most physicists suspect that some deeper principle prevents tachyons from existing in nature, though we don't yet understand what that principle might be. Another challenge to the speed limit comes from quantum mechanics and the phenomenon of quantum entanglement. When two particles become entangled, measuring one particle instantly affects the quantum state of the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance, and argued that it proved quantum mechanics was incomplete. But decades of experiments have confirmed that quantum entanglement really does create instantaneous correlations between distant particles. When you measure the spin of one entangled electron, you instantly know the spin of its partner, even if it's on the other side of the galaxy. The correlation is perfect and immediate, with no delay for information to travel between the particles. This seems to violate Einstein's speed limit, but appearances can be deceiving. The crucial insight is that quantum entanglement doesn't allow you to send usable information faster than light. The correlations are real and instantaneous, but they're also random and uncontrollable. You can't use entanglement to send a message or influence distant events in any predictable way. When you measure an entangled particle, you get a random result that's correlated with the random result your distant partner will obtain when they measure their particle. But neither of you can control what result you get, and neither can use the measurement to send information to the other. The correlations only become apparent when you compare notes through normal, slower than light communication channels. So quantum entanglement preserves the spirit of Einstein's speed limit even while violating its letter. No usable information travels faster than light, and no causal paradoxes arise. The universe maintains its logical structure while exhibiting genuinely mysterious quantum behavior that we still don't fully understand. But entanglement hints at deep connections between distant regions of space that transcend our classical notions of locality and causality. Some physicists speculate that these quantum connections might be related to the geometric structure of space-time itself, perhaps through wormholes or other exotic features predicted by Einstein's general relativity. This brings us back to gravity and the central question of our story. In Einstein's theory, gravitational effects propagate as waves at exactly the speed of light. But the underlying space-time geometry that produces these effects has more complex properties. The curvature of space-time can connect distant regions in ways that might allow for faster-than-light phenomena under extreme conditions. Consider black holes, the most extreme gravitational objects in the universe. Near a black hole's event horizon, space-time curvature becomes so severe that it can create closed time-like curves, regions where time loops back on itself. Inside the event horizon, the normal relationship between space and time breaks down entirely. Could such extreme environments provide loopholes in Einstein's speed limit? Or consider the expansion of space itself? When the universe expands, distant galaxies move away from us at speeds that can exceed the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Rather, space itself is expanding and carrying the galaxies along. Could similar effects occur in strong gravitational fields, allowing objects to effectively travel faster than light by riding expanding or contracting space-time? These questions push us to the very limits of our understanding. Einstein's speed limit seems absolute and inviolable when applied to objects moving through space or signals propagating between distant points. But space-time itself is more flexible and dynamic than Einstein originally imagined. The boundary between allowed and forbidden phenomena becomes blurry when we consider the most extreme gravitational environments in the universe. The search for faster-than-light phenomena has led physicists down many fascinating paths. Some have proposed exotic matter with negative energy density that could warp space-time in ways that permit faster-than-light travel. Others have suggested that quantum effects might allow information to tunnel through space-time at speeds exceeding light. Still others have looked for astronomical phenomena that might reveal violations of Einstein's speed limit in nature. But every proposed faster-than-light mechanism faces the same fundamental challenge: how to avoid causal paradoxes and preserve the logical structure of time. The mathematics of relativity seems to close every potential loophole, creating what physicists call the chronology protection conjecture. This suggests that the laws of physics conspire to prevent time travel and maintain causal order, even in the most extreme circumstances. Yet the universe continues to surprise us. Just when we think we understand the rules, new discoveries reveal hidden complexities and unexpected possibilities. The story of faster-than-light phenomena is far from over, and gravity continues to play a central role in our evolving understanding of space, time, and causality. But there are some strange experiments that made scientists wonder if the rules might not be as absolute as they seem. In the early 1900s, as Einstein was developing his theories of relativity, a small group of astronomers noticed something puzzling about the way planets move through the solar system. If gravity really propagated at the speed of light, as Einstein's theory suggested, then there should be subtle but measurable effects in planetary orbits. But when they looked for these effects with their most sensitive instruments, they found something unexpected. The planets behaved exactly as if gravity acted instantaneously, just as Newton had originally proposed. This wasn't just a minor discrepancy. It struck at the heart of Einstein's revolutionary new theory. If gravitational effects really took time to propagate from the Sun to the planets, then the direction of gravitational attraction should lag behind the actual position of massive objects. Earth, for example, should feel the Sun's gravity pointing not toward where the Sun is now, but toward where the Sun was 8 minutes and 20 seconds ago when light left its surface. To understand why this matters, imagine Earth orbiting around a Sun that suddenly vanished. In Newton's theory, Earth would immediately fly off in a straight line the instant the Sun disappeared. But if gravity propagates at the speed of light, Earth should continue orbiting the now non-existent Sun for another 8 minutes until the gravitational news of the Sun's disappearance finally reached our planet. The orbital mechanics would be completely different. But here's the puzzle. When astronomers calculated planetary orbits using Einstein's finite speed gravity, they predicted orbital instabilities that simply don't exist. Planets should gradually spiral away from the Sun as gravitational effects lag behind their actual positions. The solar system should be slowly falling apart. Yet after 4.5 billion years, the planets remain in nearly perfect circular and elliptical orbits, showing no signs of the instabilities that finite speed gravity should produce. This became known as the gravitational aberration problem, and it troubled physicists for decades. When light travels from a moving source to a moving observer, it exhibits aberration. appearing to come from a slightly different direction than the source's actual position. If gravity propagated like light, it should show similar aberration effects. But careful observations of planetary motion revealed no evidence of gravitational aberration whatsoever. The problem becomes even more acute when you consider binary star systems, where two massive stars orbit around their common center of mass. If gravitational effects lagged behind the actual positions of the stars, the orbital dynamics would be completely different from what we observe. The stars would experience gravitational forces pointing toward each other's past positions rather than their current positions, leading to orbital decay and eventual collision on astronomically short timescales. Yet binary star systems throughout the galaxy remain stable for millions or billions of years. The two stars orbit each other in perfect synchronization, as if each one knows exactly where the other is at every instant, not where it was when light or gravitational waves left its surface. This synchronization seems to require faster-than-light communication between the orbiting masses. Some of the most puzzling observations came from studies of our own moon. As the moon orbits Earth, it should experience gravitational forces pointing toward where Earth was 1 1/3 seconds ago, not where Earth is now. Over the course of a month-long orbital period, this lag should accumulate into measurable deviations from the moon's predicted path. But precise laser-ranging measurements of the moon's distance, accurate to within centimeters, show no evidence of any such gravitational lag effects. These observations led some physicists to propose radical alternatives to Einstein's theory. Perhaps gravity really was different from other forces. Perhaps it could somehow propagate faster than light without violating causality. Perhaps there were multiple components to gravitational interaction, with some parts acting instantaneously and others propagating at the speed of light. One of the most intriguing proposals came from physicist Tom van Flandern, who argued that gravitational effects must propagate at speeds at least 20 billion times faster than light to explain the stability of the solar system. Van Flandern pointed out that if the sun's gravitational pull on Earth really pointed toward the sun's position 8 minutes ago, Earth's orbit would be unstable and our planet would spiral into the sun within a few thousand years. Van Flandern's argument seemed compelling at first glance. Earth travels about 30 kilometers per second in its orbit around the sun. If Earth feels gravitational attraction toward where the sun was 8 minutes ago, that's a position about 15,000 kilometers away from where the sun actually is now. This misdirected gravitational pull should act like a constant braking force, gradually slowing Earth's orbital motion and causing our planet to spiral inward. But Van Flandern's analysis contained a subtle error that illustrates the complexity of Einstein's theory. He treated gravity as a force propagating through space, much like Newton's original conception, but with a finite speed. But Einstein's general relativity describes gravity very differently. It's not a force at all, but rather the curvature of space-time itself. And the curvature of space-time has properties that are much more subtle than simple force propagation. The resolution of the gravitational aberration problem lies in understanding how Einstein's field equations actually work. In general relativity, the gravitational field has two components: a static part that doesn't propagate at all, and a dynamic part that propagates as gravitational waves at the speed of light. For slowly moving objects like planets, the static component dominates, creating the illusion of instantaneous gravitational effects. Think of it this way. The sun's mass creates a permanent depression in the fabric of space-time, like a bowling ball resting on a stretched rubber sheet. This depression extends throughout the solar system and doesn't need to propagate anywhere because it's already there. Planets simply follow the curved paths defined by this static space-time geometry. Only when the sun's mass distribution changes rapidly do gravitational waves carry information about those changes outward at the speed of light. This means that for most astronomical situations, gravity appears to act instantaneously, not because it violates Einstein's speed limit, but because the relevant gravitational effects are already built into the geometry of space-time. The planets don't wait for gravitational signals to arrive from the Sun, because they're not responding to signals at all. They're responding to the local curvature of space-time right where they are. But this explanation, while mathematically correct, still leaves many physicists feeling unsatisfied. It seems to push the mystery of gravitational propagation one level deeper without truly resolving it. How does the static gravitational field know about the current position of massive objects if no information can travel faster than light? How can space-time curvature remain synchronized with moving masses without some form of faster-than-light communication? These questions become even more puzzling when you consider what happens during rapid changes in gravitational fields. When a massive star collapses to form a black hole, its gravitational effects should propagate outward as waves at the speed of light. But the transition from normal stellar gravitational field to black hole gravitational field seems to occur smoothly, without the discontinuities or instabilities you might expect from finite speed propagation. Similarly, when two black holes spiral into each other and merge, they create violent disturbances in space-time that ripple outward as gravitational waves. But the orbital dynamics leading up to the merger seem to follow Einstein's equations perfectly, with no evidence of gravitational lag effects that would destabilize the orbit prematurely. The two black holes dance together in perfect synchronization until the very moment they touch. Some physicists have proposed that these observations hint at hidden aspects of Einstein's theory that we don't yet fully understand. Perhaps space-time has non-local properties that allow distant regions to remain correlated without explicit communication. Perhaps the geometry of space-time contains information about future as well as past events, creating a kind of temporal connectivity that transcends our usual notions of causality. Others have suggested that the apparent instantaneous nature of gravity might be explained by quantum mechanical effects. In quantum field theory, virtual particles can temporarily violate conservation laws and even exceed the speed of light, as long as they exist for such short times that the violations cannot be directly observed. Perhaps gravitational interactions are mediated by virtual gravitons that can travel faster than light over short distances, creating the illusion of instantaneous action at astronomical scales. But all of these proposals remain highly speculative. The mainstream interpretation of Einstein's theory provides mathematically consistent explanations for all observed gravitational phenomena, including the apparent instantaneous nature of planetary motion. The key insight is that gravity in general relativity is fundamentally different from other forces. It's not something that propagates between objects, but rather the geometric structure of space-time itself. This geometric interpretation explains why planets don't exhibit gravitational aberration effects. They're not receiving gravitational signals from the Sun. Instead, they're following geodesics through curved space-time, and those geodesics are determined by the local geometry of space-time at each point along the planet's path. The curvature reflects the Sun's mass and position, but it does so through the mathematical structure of Einstein's field equations, rather than through signals propagating at finite speeds. Yet questions remain about how this local curvature stays synchronized with distant masses. The field equations are local, meaning they relate the curvature at each point to the matter and energy at that same point. But somehow, the curvature throughout the solar system remains precisely coordinated with the positions and motions of all the massive objects it contains. This coordination seems to require some form of faster-than-light correlation, even if no information or energy travels faster than light. The debate over gravitational propagation speed has practical implications for our understanding of the universe. If gravity really did propagate much faster than light, it would open up possibilities for faster-than-light communication, and perhaps even time travel. civilizations with sufficiently advanced technology might be able to exploit gravitational effects to send messages across the galaxy instantly, or to detect events before light from those events could reach them. But if gravity strictly obeys Einstein's speed limit, then these exotic possibilities are ruled out. The universe maintains a rational causal structure, where effects cannot precede their causes, and information cannot travel faster than light through any physical mechanism. The apparent instantaneous nature of gravitational effects reflects the geometric structure of spacetime, rather than faster-than-light signal propagation. The resolution of this debate would come from an unexpected source: the direct detection of gravitational waves themselves. If Einstein was right about gravitational propagation speed, then gravitational waves should travel at exactly the speed of light, no faster and no slower. But measuring the speed of gravitational waves would require detecting them first, and that technological challenge would take nearly a century to overcome. So is there a case that gravity does move faster than light? The observational evidence seemed ambiguous, with planetary motion suggesting instantaneous effects, while Einstein's theory demanded finite propagation speeds. The answer would ultimately come from catching gravitational waves in the act of traveling across the cosmos. September 14th, 2015. At 9:51 and 16 seconds Coordinated Universal Time, something extraordinary rippled through the fabric of space-time itself. Two black holes, each about 30 times more massive than our Sun, had been spiraling around each other for millions of years in a galaxy over 1 billion light-years away. In their final moments, they accelerated to incredible speeds, reaching nearly half the speed of light before colliding and merging into a single, even more massive black hole. The collision released more energy in gravitational waves than all the stars in the observable universe emit in light. For a brief fraction of a second, this cosmic cataclysm was the most powerful source of gravitational radiation in the entire universe. The waves it created began racing outward through space at exactly the speed of light, carrying the news of this distant apocalypse toward Earth. 1 billion years later, those waves finally reached our planet. They passed through the Earth itself as if it were made of gossamer, barely interacting with matter at all. But they did something far more subtle and profound. They stretched and compressed space itself by amounts so tiny that they defied comprehension. The entire Earth expanded and contracted rhythmically as the waves passed, but by distances smaller than 1/10,000th the width of a proton. This infinitesimal stretching and squeezing of space was detected by two of the most sensitive scientific instruments ever built, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, known as LIGO. One detector sits in Hanford, Washington, while its twin operates in Livingston, Louisiana. Each consists of two perpendicular arms, each arm stretching 4 kilometers in length, with laser beams bouncing back and forth between mirrors at the ends. When a gravitational wave passes through a LIGO detector, it stretches space in one direction while compressing it in the perpendicular direction. This causes tiny changes in the distances the laser beams travel, which in turn creates interference patterns that can be measured with extraordinary precision. The detectors are so sensitive that they can measure changes in length smaller than 1/10,000th the width of a proton across a 4-kilometer baseline. The September 14th detection, which scientists named GW150914 after the date it occurred, marked the beginning of a new era in astronomy. For the first time in history, humans had directly observed gravitational waves, confirming one of Einstein's most exotic predictions, a full century after he first proposed their existence. But the discovery had implications far beyond just validating general relativity. It provided the most precise test ever of how fast gravity travels. Einstein's equations were unambiguous. Gravitational waves should propagate at exactly the speed of light, no faster and no slower. If gravity could somehow travel faster than light, as some theories suggested, then gravitational waves should arrive at Earth before light from the same cosmic event. Conversely, if gravity traveled slower than light, the waves should arrive after any accompanying light signals. The LIGO detection offered no opportunity to test this prediction because black hole mergers produce no light. When two black holes spiral together and collide, they create purely gravitational fireworks, invisible to conventional telescopes. The event that created GW 150914 was completely dark, except for its gravitational wave emission. There was no light signal to compare with the gravitational wave arrival time. But LIGO scientists knew that future detections might involve different types of cosmic collisions that would produce both gravitational waves and light. Neutron stars, the ultra-dense remnants of massive stellar explosions, can merge just like black holes. But unlike black holes, neutron star mergers are expected to produce brilliant displays of light across the entire electromagnetic spectrum, from radio waves to gamma rays. The opportunity to test gravitational wave propagation speed came sooner than anyone expected. On August 17, 2017, LIGO detected another gravitational wave signal, this one designated GW170817. The signal had all the characteristics of a neutron star merger. It lasted much longer than previous black hole detections, sweeping upward in frequency as the two stars spiraled closer together before finally touching and merging. But this time, LIGO wasn't alone. The European Virgo detector had recently joined the gravitational wave network, and all three detectors observed the merger simultaneously. The combination of three detectors allowed scientists to triangulate the source's position in the sky with unprecedented accuracy, pinpointing the merger to a small region of the southern constellation Hydra. Within seconds of the gravitational wave detection, astronomical alerts went out to observatories around the world. If this really was a neutron star merger, it should produce a brilliant explosion of light that would be visible for days or weeks after the collision. Dozens of telescopes swung toward the indicated region of sky, searching for the optical counterpart to the gravitational wave event. Meanwhile, something else was happening that would prove crucial for testing gravitational wave propagation speed. The Fermi Gamma Ray Space Telescope, orbiting high above Earth's atmosphere, had detected a short burst of gamma rays coming from the same region of sky as the gravitational wave source. The gamma ray burst, designated GRB 170817A, began just 1.7 seconds after the gravitational waves reached Earth. This tiny time delay between gravitational waves and gamma rays provided the most precise test of gravitational wave propagation speed ever conducted. The neutron star merger had occurred in galaxy NGC 4993, approximately 130 million light-years from Earth. Both the gravitational waves and the gamma rays had traveled this enormous distance, racing through space for 130 million years before reaching our planet. If gravitational waves traveled faster than light, they should have arrived more than a second before the gamma rays. If they traveled slower than light, they should have arrived more than a second after the gamma rays. Instead, they arrived within 1.7 seconds of each other, after a journey lasting 130 million years. This represented a timing accuracy of better than 1 part in 100 billion. The implications were staggering. Einstein's prediction that gravitational waves travel at exactly the speed of light had been confirmed to extraordinary precision. Any theory suggesting that gravity could propagate faster than light was dealt a devastating blow. The cosmic speed limit applied to gravity just as strictly as it applied to light itself. But the story became even more remarkable as optical telescopes began finding the visible counterpart to the gravitational wave source. About 11 hours after the merger, the SWOPE supernova survey at Las Campanas Observatory in Chile spotted a new point of light in galaxy NGC 4993. The light was exactly where the gravitational wave triangulation had predicted, confirming that astronomers had found the optical signature of colliding neutron stars. This optical counterpart, designated AT2017 GFO, provided an unprecedented view of cosmic alchemy in action. The merger had created a kilonova, an explosion powered by the radioactive decay of newly synthesized heavy elements. For the first time, scientists could observe the cosmic factories where nature forges gold, platinum, uranium, and other heavy elements through rapid neutron capture processes. The multi-messenger observations of GW170817 represented a triumph of modern astronomy. The same cosmic event had been observed in gravitational waves, gamma rays, visible light, infrared radiation, and radio waves. Each type of radiation told a different part of the story, but they all arrived at Earth within hours of each other after traveling for 130 million years. This remarkable concordance provided the strongest evidence yet that all fundamental interactions respect Einstein's cosmic speed limit. Electromagnetic radiation in all its forms, from radio waves to gamma rays, travels at the speed of light. Now gravitational waves had been shown to travel at exactly the same speed, within experimental uncertainties of 1 part in 100 billion billion. The precision of this measurement effectively ruled out a vast range of alternative theories of gravity. Any theory that predicted faster than light gravitational propagation would have to explain why gravitational waves from GW170817 didn't arrive hours, days, or even years before the associated gamma ray burst. The universe seemed to enforce Einstein's speed limit with remarkable consistency, but the discoveries didn't stop there. In the months following GW170817, astronomers detected the optical counterpart fading gradually as the radioactive glow of newly minted heavy elements slowly cooled. Spectroscopic observations revealed the unmistakable signatures of gold and platinum being synthesized in real time, confirming theoretical predictions about how the heaviest elements in the periodic table are created. The neutron-star merger also provided insights into the nature of matter under the most extreme conditions imaginable. Neutron stars are so dense that a teaspoon of their material would weigh as much as Mount Everest. When two such objects collide, they create conditions of temperature and density that cannot be reproduced in any laboratory on Earth. The gravitational waves and electromagnetic radiation from the merger carried detailed information about how matter behaves under these extreme conditions. Perhaps most importantly, the multi-messenger observation of GW170817 demonstrated the power of gravitational wave astronomy to reveal previously hidden aspects of the universe. Traditional astronomy relies on electromagnetic radiation, which can be absorbed, scattered, or obscured by intervening matter. But gravitational waves pass through matter almost unimpeded, carrying pristine information about their sources across cosmic distances. The combination of gravitational wave and electromagnetic observations provided a more complete picture of cosmic events than either type of observation could achieve alone. The gravitational waves revealed the masses and spins of the merging neutron stars, while the electromagnetic radiation showed the composition and structure of the material ejected during the collision. Together, they painted a detailed portrait of one of the most violent events in the universe. The success of multi-messenger astronomy also opened new possibilities for testing fundamental physics. Future detections of neutron star mergers could provide even more precise measurements of gravitational wave propagation speed, potentially revealing tiny deviations from Einstein's predictions that might point toward new physics beyond general relativity. But for now, the message from GW170817 was clear and unambiguous. Gravitational waves travel at exactly the speed of light, confirming Einstein's century-old prediction with breathtaking precision. The cosmic speed limit applies to all fundamental interactions, including gravity itself. The universe maintains its rational causal structure, where effects cannot precede their causes and information cannot travel faster than light. This definitive measurement of gravitational wave speed seemed to close the door on theories proposing faster than light gravity. But as we'll see, the story of gravitational propagation has more subtle layers. While dynamic gravitational effects clearly travel at the speed of light, the static geometric structure of space-time might have different properties entirely. Yet some physicists still wonder whether the geometry of gravity itself could be instantaneous, even if gravitational waves respect the speed limit. The detection of gravitational waves traveling at exactly the speed of light seemed to settle the debate about gravitational propagation once and for all. Einstein was right. Gravity respects the cosmic speed limit, just like every other fundamental force. But this victory for relativity actually deepened one of the most puzzling aspects of gravitational theory. If gravitational effects take time to propagate, why do planets orbit as if they feel the sun's gravity instantaneously? To understand this apparent contradiction, we need to dive deeper into the subtle distinction between two very different aspects of Einstein's gravitational theory. On one hand, there are gravitational waves, dynamic ripples in space-time that carry energy and information at the speed of light. On the other hand, there are static gravitational fields, the permanent curvature of space-time around massive objects that doesn't propagate at all, because it's already everywhere it needs to be. Think of this distinction in terms of a familiar analogy. Imagine a massive bowling ball resting on a stretched rubber sheet. The ball creates a depression in the sheet that extends far beyond the ball itself. This depression is like a static gravitational field. It doesn't need to travel anywhere because it's simply the shape of the sheet around the ball. If you roll a marble near the bowling ball, it will curve toward the depression, following the geometry of the distorted sheet. Now imagine what happens if you suddenly jiggle the bowling ball up and down. This creates waves that ripple outward across the sheet at a finite speed. These waves are like gravitational waves. They carry energy and information about the ball's motion, and they take time to reach distant parts of the sheet. But the underlying depression caused by the ball's mass remains in place, continuing to guide the motion of nearby marbles even while the waves are propagating outward. Einstein's theory of general relativity describes gravity in exactly this way. Massive objects like the sun create a permanent curvature in the fabric of space-time. This curvature extends throughout the solar system and defines the paths that planets follow as they orbit. The curvature itself doesn't propagate because it's not going anywhere. It's simply the shape of space-time in the presence of the sun's mass. But when the sun's mass distribution changes rapidly, perhaps due to internal convulsions or external disturbances, those changes create gravitational waves that ripple outward through space-time at the speed of light. The waves carry information about the changes in the sun's gravitational field, but they're superimposed on top of the underlying static curvature that was already there. This dual nature of gravity resolves the apparent paradox of instantaneous planetary motion. Planets don't respond to gravitational signals traveling from the sun. Instead, they follow geodesics through the curved space-time geometry that the sun's mass creates. That geometry is already established throughout the solar system, having been put in place when the solar system first formed 4.5 billion years ago. To make this more concrete, consider what happens when Earth moves in its orbit around the sun. From Earth's perspective, it's simply following the straightest possible path through four-dimensional space-time. The curvature of space-time caused by the sun's mass makes this straight line path appear curved when projected into our familiar three-dimensional space, creating Earth's elliptical orbit. Earth doesn't need to wait for gravitational signals to arrive from the sun, because it's not responding to signals at all. It's responding to the local geometry of space-time right where it is. That geometry encodes information about the sun's mass and position, but it does so through the mathematical structure of Einstein's field equations, rather than through signals propagating at finite speeds. But here's where things get subtle. The local curvature of space-time at Earth's position does depend on the Sun's current mass and position, not its past configuration. This seems to require some form of instantaneous correlation between distant regions of space-time. How can the geometry near Earth stay synchronized with the Sun's actual position if no information travels faster than light? The answer lies in understanding how Einstein's field equations actually work. These equations are what physicists call local differential equations. They relate the curvature of space-time at each point to the distribution of matter and energy at that same point. But the solutions to these equations can have global properties that extend across vast regions of space and time. When you solve Einstein's equations for a massive object like the Sun, you get a solution that describes the curvature of space-time throughout the entire solar system. This solution automatically ensures that the geometry remains consistent everywhere, with the curvature at each point reflecting the appropriate combination of local and distant matter distributions. The key insight is that these solutions represent the equilibrium configuration of space-time in the presence of matter. Just as a soap bubble automatically assumes a spherical shape that minimizes surface tension, space-time automatically assumes a curved configuration that satisfies Einstein's field equations. The geometry doesn't need to propagate from one region to another because it's determined by the global solution to the field equations. This is fundamentally different from how we usually think about cause and effect. In most physical situations, causes at one location produce effects at distant locations through signals or influences that propagate at finite speeds. But in Einstein's theory, the presence of matter at one location contributes to the global geometry of space-time in a way that doesn't require signal propagation. To understand this better, consider the mathematical structure of Einstein's field equations. On one side of the equations, you have terms describing the curvature of space-time. On the other side, you have terms describing the distribution of matter and energy. The equations say that these two sides must be equal at every point in space-time. But solving these equations requires considering the entire space-time manifold simultaneously. You can't determine the curvature at one point without knowing the matter distribution everywhere else, because the geometry must be globally consistent. This global constraint is what ensures that the gravitational field remains synchronized with the current positions of massive objects. However, this synchronization only works for static or slowly changing mass distributions. When masses accelerate rapidly, they create dynamic changes in the space-time curvature that must propagate outward as gravitational waves. These waves carry information about the changing mass distribution at the speed of light, updating the global geometry as they spread. The solar system represents an excellent example of the static case. The Sun and planets move relatively slowly compared to the speed of light, and their mass distributions change gradually over astronomical timescales. Under these conditions, the space-time geometry remains in a quasi-static equilibrium that tracks the current positions of the masses without requiring signal propagation. But consider a more extreme scenario. Two black holes spiraling rapidly toward each other before merging. In this case, the masses are accelerating violently and changing their configuration on timescales much shorter than the light travel time between them. The space-time geometry cannot remain in static equilibrium, and gravitational waves become essential for maintaining consistency between distant regions. During the final moments before black hole merger, the geometry of space-time becomes highly dynamic. Gravitational waves carry information about the changing mass distribution throughout the surrounding region, updating the local curvature as they pass. The familiar distinction between static fields and propagating waves breaks down in these extreme situations. This brings us to one of the deepest mysteries in gravitational physics: the relationship between local and global properties of space-time. Einstein's field equations are local, relating quantities at each point to other quantities at the same point. Yet the solutions to these equations have global properties that seem to require instantaneous coordination across vast distances. Some physicists interpret this as evidence for hidden non-local aspects of general relativity. Perhaps space-time has intrinsic correlations that transcend the usual limitations of finite signal speeds. Perhaps the geometry of space-time emerges from more fundamental quantum processes that don't respect classical notions of locality. Others argue that the apparent non-locality is just a reflection of how we choose to describe gravitational phenomena. The field equations themselves are completely local, and all physical processes respect the speed of light limit. The global properties of space-time solutions are mathematical consequences of these local equations, not evidence for faster-than-light influences. This debate touches on some of the most fundamental questions in theoretical physics. What is the nature of space-time itself? Is it a fundamental aspect of reality, or does it emerge from more basic constituents? How do local interactions give rise to global geometric properties? These questions become even more pressing when we consider attempts to unify general relativity with quantum mechanics. In quantum field theory, the vacuum state of spacetime is far from empty. It's filled with virtual particles that constantly appear and disappear, creating quantum fluctuations in the geometry itself. These quantum effects might provide new mechanisms for correlating distant regions of spacetime in ways that classical general relativity doesn't capture. Some theories of quantum gravity suggest that spacetime might emerge from networks of quantum entanglement between microscopic degrees of freedom. In these approaches, the geometric properties of spacetime would reflect the pattern of quantum correlations in the underlying quantum state. Since quantum entanglement can create instantaneous correlations between distant systems, this might explain how spacetime geometry remains synchronized across vast distances. But these ideas remain highly speculative. The mathematical challenges of combining general relativity with quantum mechanics are formidable, and we're still far from a complete theory of quantum gravity. For now, the distinction between static gravitational fields and propagating gravitational waves provides the best available explanation for the apparent instantaneous nature of gravitational effects. The key insight is that what we perceive as instantaneous gravitational attraction is really just the manifestation of space-time geometry that was established in the distant past and has remained stable ever since. The Sun's gravitational field doesn't reach out and grab Earth instantaneously. Instead, Earth moves through a region of curved spacetime whose geometry reflects the Sun's presence. This geometric interpretation explains why gravitational effects seem instantaneous for slowly moving astronomical objects, while clearly propagating at finite speeds for rapidly changing systems. The geometry adapts to slow changes without requiring wave propagation, but responds to rapid changes through gravitational waves that respect Einstein's speed limit. Yet questions remain about the ultimate nature of this geometric explanation. How does space-time know what geometry to assume in response to the distribution of matter? What prevents inconsistencies from arising between the geometry in different regions? And how do quantum effects modify the classical picture of smooth space-time curvature? So if gravity obeys the speed of light limit, could something deeper be at play in the quantum realm? Deep beneath the smooth curves of Einstein's spacetime lies a hidden realm where the familiar laws of physics break down completely. At distances smaller than 10 to the power of minus 35 meters and times shorter than 10 to the power of minus 43 seconds, the very concepts of space and time lose their meaning. This is the Planck scale, named after the German physicist Max Planck, where quantum mechanics and general relativity clash in a fundamental conflict that has puzzled physicists for nearly a century. At these unimaginably tiny scales, space-time itself becomes grainy and turbulent. The smooth fabric that Einstein described as curved by mass and energy transforms into a roiling foam of virtual particles, fluctuating geometries, and quantum uncertainties. Space and time, which seem so solid and reliable in our everyday experience, reveal themselves to be emergent properties of something far stranger and more fundamental. This quantum foam, as physicists call it, represents one of the greatest unsolved mysteries in modern physics. We know that quantum mechanics governs the behavior of matter and energy at microscopic scales, while general relativity describes the large-scale structure of space-time. But nobody knows how to combine these two theories into a single, consistent framework that works at all scales. The problem isn't just technical or mathematical, it's conceptual. Quantum mechanics is built on the idea that physical quantities come in discrete packets or quanta, and that measuring a quantum system fundamentally disturbs it in unpredictable ways. General relativity, by contrast, describes space-time as a smooth, continuous manifold whose curvature can be measured precisely without affecting the geometry itself. These two worldviews seem fundamentally incompatible. In quantum mechanics, the very act of observation changes reality. In general relativity, space-time provides a fixed stage on which physical events unfold. In quantum mechanics, uncertainty and probability are fundamental features of nature. In general relativity, the geometry of space-time is deterministic and predictable. Yet both theories are spectacularly successful within their respective domains. Quantum mechanics explains the behavior of atoms, molecules, and subatomic particles with incredible precision. It underlies all of modern electronics, from computer chips to lasers to magnetic resonance imaging. General relativity describes the motion of planets, the evolution of stars, and the expansion of the universe with equal accuracy. The clash between these theories becomes acute when we try to understand gravity at quantum scales. According to quantum field theory, all forces should be mediated by quantum particles. The electromagnetic force is carried by photons, the weak nuclear force by W and Z bosons, the strong nuclear force by gluons. By analogy, gravity should be mediated by hypothetical particles called gravitons. But gravitons, if they exist, would be almost impossible to detect. Gravity is by far the weakest of the fundamental forces. A single graviton carries so little energy that it would interact with matter incredibly rarely. Detecting individual gravitons would require particle accelerators millions of times more powerful than anything we could ever build on Earth. More troubling, attempts to construct a quantum theory of gravity run into severe mathematical difficulties. When physicists try to calculate quantum corrections to Einstein's field equations, they get infinite answers that don't make physical sense. Unlike other quantum field theories, where similar infinities can be removed through mathematical techniques called renormalization, quantum gravity seems to resist all attempts at taming its mathematical pathologies. These problems have led physicists to propose radical alternatives to conventional approaches to quantum gravity. Some of these alternatives suggest that space-time itself might not be fundamental, but rather an emergent property of more basic quantum degrees of freedom. In these theories, the smooth geometry that we observe at large scales would be like the surface of a calm lake, hiding the chaotic quantum fluctuations that rage beneath. One of the most ambitious approaches is string theory, which proposes that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. These strings exist in a space with more than the usual 3 spatial dimensions, with the extra dimensions curled up so tightly that we can't perceive them directly. Different vibration patterns of the strings correspond to different particles, including a hypothetical graviton that would carry the gravitational force. String theory, offers elegant solutions to many of the mathematical problems that plague other approaches to quantum gravity. The extended nature of strings smooths out the violent quantum fluctuations that cause infinities in point particle theories. The theory also naturally incorporates gravity alongside the other fundamental forces, suggesting a path toward the ultimate goal of physics, a theory of everything that unifies all forces and particles into a single mathematical framework. But string theory comes with its own profound mysteries. The theory requires space-time to have 10 or 11 dimensions, far more than the 4 that we directly observe. The extra dimensions must be compactified in specific ways to produce the physics that we see in our 3-dimensional world. But there are countless ways to perform this compactification, leading to a vast landscape of possible universes with different physical laws. More troubling for our story, string theory suggests that the concept of locality, the idea that objects can only directly influence their immediate neighbors, might be an illusion. In string theory, strings can interact with each other across macroscopic distances through quantum entanglement and other non-local quantum effects. This raises the possibility that gravitational influences might propagate through hidden dimensions or quantum channels that bypass the usual speed of light limitations. Another radical approach to quantum gravity is loop quantum gravity, which takes the opposite tack from string theory. Instead of embedding space-time in higher dimensions, loop quantum gravity proposes that space itself is quantized at the Planck scale. Just as matter comes in discrete atoms, space might come in discrete chunks that cannot be subdivided further. In loop quantum gravity, the smooth space-time of general relativity emerges from a network of quantum loops and nodes, like a fabric woven from quantum threads. The geometry that we observe at large scales represents the collective behavior of countless microscopic quantum degrees of freedom, much like the temperature and pressure of a gas emerge from the random motions of individual molecules. This quantization of space has profound implications for how we think about gravitational propagation. If space consists of discrete units, then information about gravitational changes might propagate through the quantum network in ways that don't necessarily respect the classical speed of light limit. The discrete structure might allow for quantum tunneling effects that permit faster than light information transfer under special circumstances. Both string theory and loop quantum gravity remain highly speculative. Neither approach has yet made testable predictions that could be verified through experiments or observations. The energy scales where quantum gravity effects become important are far beyond anything accessible with current technology. We can only probe these theories indirectly by studying their implications for cosmology, black hole physics, and other extreme gravitational phenomena. But some physicists believe that quantum gravity effects might leave observable signatures in the cosmic microwave background, the afterglow of the Big Bang that fills the entire universe. Quantum fluctuations during the earliest moments of cosmic inflation might have been amplified to macroscopic scales, creating patterns in the microwave background that could reveal the quantum structure of space-time itself. Others look to black holes as natural laboratories for testing quantum gravity theories. When matter falls into a black hole, it encounters regions where space-time curvature becomes extreme and quantum effects should become important. The radiation that black holes emit, known as Hawking radiation, might carry information about the quantum gravitational processes occurring near the event horizon. Perhaps most intriguingly, some quantum gravity theories suggest that the information paradox associated with black holes might be resolved through non-local quantum effects that allow information to escape from black holes faster than light. In these scenarios, quantum entanglement creates hidden channels that connect the interior and exterior of black holes, permitting information transfer that bypasses the classical constraints imposed by the event horizon. These ideas remain at the cutting edge of theoretical physics, with no experimental confirmation and often contradictory predictions from different approaches. but they hint at a deeper reality where the familiar concepts of space, time, and locality might be approximations that break down under extreme conditions. The search for quantum gravity has also revealed unexpected connections between gravity and other areas of physics. The holographic principle, emerging from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on its boundary surface. This implies that our three-dimensional experience of space might be a projection of more fundamental processes occurring on a two-dimensional surface. Even more remarkably, recent work has suggested deep connections between gravity and quantum entanglement. The Einstein-Rosen bridge, a hypothetical wormhole connecting distant regions of space-time, might be equivalent to quantum entanglement between particles on opposite sides of the wormhole. This correspondence, known as ER equals EPR, suggests that the geometry of space-time and the quantum correlations between particles might be two aspects of the same underlying phenomenon. If this correspondence is correct, then quantum entanglement might literally create the geometry of space-time. Regions that are highly entangled would correspond to regions connected by short wormholes, while regions with little entanglement would be separated by large distances. The familiar metric of space-time, which determines how distances and times are measured, would emerge from the pattern of quantum entanglement in the underlying quantum state. This would have profound implications for how gravitational effects propagate. Instead of traveling through space-time, gravitational influences might propagate through the network of quantum entanglement that creates space-time in the first place. This entanglement network might allow for correlations that transcend the usual speed of light limitations, creating effective faster-than-light communication through quantum channels. But all of these ideas remain highly speculative and mathematically challenging. The path from quantum entanglement to emergent spacetime involves complex mathematical machinery that few physicists fully understand. The predictions of these theories are often ambiguous or contradictory, making it difficult to determine which approaches are on the right track. Moreover, even if space-time does emerge from quantum entanglement, it's not clear that this would allow for observable violations of Einstein's speed limit. The quantum correlations that create space-time geometry might be hidden from direct observation, influencing the large-scale structure of space and time without permitting faster-than-light information transfer. The quest to understand quantum gravity continues to push the boundaries of human knowledge. Every proposed solution raises new questions and reveals new mysteries. The mathematical frameworks required to describe quantum spacetime are so complex that they challenge our basic intuitions about reality itself. Yet the stakes couldn't be higher. A successful theory of quantum gravity would revolutionize our understanding of the universe, potentially revealing the ultimate nature of space, time, matter, and energy. It might explain the origin of the universe, the fate of black holes, and the fundamental constants that determine the properties of physical reality. For our story about gravitational propagation, quantum gravity theories suggest that the question of whether gravity travels faster than light might not have a simple answer. At macroscopic scales, where space-time behaves classically, gravitational effects clearly propagate at the speed of light. But at microscopic scales, where quantum effects dominate, the very concepts of space, time, and signal propagation might need to be completely reconsidered. Which leads to the deepest mystery. Can the universe support instant influence through quantum entanglement? And how does this relate to the propagation of gravitational effects? In 1935, Albert Einstein found himself in an uncomfortable position. The quantum theory he had helped create was predicting phenomena so strange that even he couldn't accept them. Working with colleagues Boris Podolsky and Nathan Rosen, Einstein published a paper that would haunt physics for decades. They described a thought experiment involving two particles that had once interacted, but were now separated by vast distances. According to quantum mechanics, measuring one particle would instantly affect the other, no matter how far apart they were. Einstein called this spooky action at a distance and argued that it proved quantum mechanics was incomplete. Surely, he reasoned, the particles must carry hidden information that predetermined the results of any measurement. The alternative was too disturbing to contemplate, that nature really did permit instantaneous influences across arbitrary distances, violating the very foundations of relativity theory. What Einstein couldn't have imagined was that this spooky action would not only prove to be real, but might also hold the key to understanding the deepest mysteries of space, time, and gravity itself. Quantum entanglement, as physicists now call this phenomenon, has emerged as one of the most powerful and puzzling features of quantum mechanics. And recent discoveries suggest it might be intimately connected to the geometry of space-time in ways that could revolutionize our understanding of how gravitational effects propagate. To understand quantum entanglement, imagine two electrons that are created together in a specific quantum state. The laws of quantum mechanics dictate that each electron must have a property called spin, which can point either up or down. But before measurement, neither electron has a definite spin direction. Instead, each exists in a quantum superposition of both up and down states simultaneously. The remarkable thing about entangled particles is that their quantum states remain correlated even after they're separated. If you measure the first electron and find it spinning up, you instantly know that the second electron must be spinning down, regardless of how far away it is. The correlation is perfect and immediate, transcending the limitations of space and time. This isn't just theoretical speculation. Physicists have confirmed quantum entanglement in countless experiments over the past several decades. They've created entangled photons, atoms, and even macroscopic objects, demonstrating that the correlations persist across laboratory distances and beyond. Some experiments have verified entanglement between particles separated by hundreds of kilometers, with the correlations appearing faster than light could travel between them. But here's the crucial twist that preserves Einstein's relativity. While the correlations are instantaneous, they can't be used to send information faster than light. When you measure an entangled particle, you get a random result that's correlated with the random result your distant partner will obtain. But neither of you can control what result you get, and neither can use the measurement to send a signal to the other. The information about the correlation only becomes apparent when you compare notes through normal, slower than light communication channels. Until then, each measurement looks completely random to the individual observers. It's only when they come together and compare their results that the spooky correlation reveals itself. This preservation of causality has allowed physicists to accept quantum entanglement while maintaining Einstein's prohibition against faster-than-light signaling. The quantum correlations are real and instantaneous, but they're also fundamentally random and uncontrollable. They create connections between distant regions of space without violating the rational structure of space-time. Yet the very existence of quantum entanglement suggests that our classical notions of locality and separability might be fundamentally wrong. If particles can remain correlated across arbitrary distances without any physical connection between them, then the universe must have hidden aspects that transcend our everyday understanding of space and time. This mystery deepened in the 1960s when physicist John Bell proved that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. Bell's theorem showed that the correlations between entangled particles are stronger than anything that could be explained by particles carrying predetermined information. The particles really do seem to communicate instantaneously, even though this communication can't be used to send controllable signals. Bell's work led to a new understanding of quantum mechanics that emphasized its fundamentally non-local character. The quantum world operates according to principles that have no classical analog. Particles don't have definite properties until they're measured, and the act of measurement on one particle can instantly affect the properties of distant particles with which it's entangled. This non-locality of quantum mechanics has profound implications for our understanding of space and time. If quantum correlations can transcend spatial separation, then perhaps space itself is not as fundamental as we once thought. Maybe the three-dimensional space we perceive is an emergent property of more basic quantum relationships that don't respect classical notions of distance and locality. Some physicists have taken this idea to its logical extreme, proposing that space-time itself emerges from patterns of quantum entanglement. In these theories, the geometry of space and time reflects the structure of quantum correlations in an underlying quantum state. Regions that are highly entangled correspond to regions that are close together in space-time, while regions with little entanglement are far apart. This emergence of space-time from entanglement might explain some of the puzzling features of gravity that we've encountered throughout our story. If gravitational effects are really manifestations of space-time geometry, and if that geometry emerges from quantum entanglement, then gravitational correlations might inherit the non-local properties of quantum entanglement itself. The idea that entanglement creates space-time gained credibility from studies of black holes and their mysterious properties. Black holes have temperatures and entropies that seem to be encoded on their surface areas rather than in their volumes. This suggests that the information inside a black hole might be holographically related to information on its boundary, much like a three-dimensional hologram is encoded on a two-dimensional surface. The holographic principle, as this idea is known, implies that the physics inside any region of space can be completely described by quantum information living on the boundary of that region. The three-dimensional bulk of space would be redundant, emerging from the two-dimensional boundary physics through quantum entanglement between different parts of the boundary. But the most dramatic connection between entanglement and space-time came from a remarkable conjecture proposed by physicists Juan Maldacena and Leonard Susskind in 2013. They suggested that Einstein-Rosen bridges, the wormholes that connect distant regions of space-time, might be equivalent to quantum entanglement between particles on opposite sides of the wormhole. This correspondence, known as ER equals EPR, after Einstein and Rosen's initials and those of the Einstein-Podolsky-Rosen paradox, would mean that every instance of quantum entanglement creates a tiny wormhole in space-time. When two particles become entangled, they would be connected not just by abstract quantum correlations, but by an actual geometric tunnel through the fabric of space and time. If ER equals EPR is correct, then the network of quantum entanglement that permeates the universe would correspond to a vast web of microscopic wormholes connecting every entangled particle to its partners. The geometry of space-time would literally be woven from quantum correlations, with the familiar metric of general relativity emerging as a large-scale approximation to this underlying quantum geometry. This would have revolutionary implications for how gravitational effects propagate. Instead of traveling through space-time as waves or manifesting as static curvature, gravitational influences might propagate through the network of entanglement wormholes that create space-time in the first place. The speed of gravitational propagation would depend on the structure of this quantum network rather than on the classical geometry of space-time. In principle, this could allow for faster-than-light gravitational effects under special circumstances. If two regions of space are connected by a dense network of entanglement wormholes, gravitational influences might be able to propagate between them faster than light could travel through the classical space-time that separates them. The quantum geometry might provide shortcuts that bypass the usual constraints of relativity. But extracting observable consequences from these ideas has proved extraordinarily difficult. The mathematics of emergent space-time involves sophisticated techniques from quantum field theory, string theory, and algebraic geometry that that push the boundaries of human mathematical understanding. Even defining what it means for space-time to emerge from entanglement requires concepts that didn't exist until recently. Moreover, most approaches to emergent space-time suggest that the quantum correlations responsible for creating geometry are hidden from direct observation. The entanglement that weaves space-time together might not be accessible to local observers, who would only see the classical geometry that emerges at large scales. Any faster-than-light effects would be buried in the quantum substrate and wouldn't permit controllable faster-than-light communication. This hidden nature of geometric entanglement might explain why we observe gravitational effects propagating at the speed of light in all practical situations. The classical space-time that emerges from quantum entanglement would naturally inherit the causal structure of the underlying quantum theory, which preserves Einstein's speed limit for observable signals, even while allowing for non-local quantum correlations. Yet some theorists have proposed scenarios where the quantum structure of space-time might become observable under extreme conditions. Near black holes, in the early universe, or in other environments where space-time curvature becomes extreme, the distinction between classical geometry and quantum entanglement might break down. In these situations, the underlying quantum nature of space-time might reveal itself through observable violations of classical relativity. The study of quantum entanglement has also revealed unexpected connections between information theory and gravitational physics. The amount of entanglement between different regions of space seems to be related to the area of the surfaces that separate those regions, echoing the holographic principle's emphasis on boundary areas. This suggests that the information content of space-time might be fundamentally limited by geometric constraints. Even more remarkably, recent work has shown that quantum error correction, the techniques used to protect quantum information from noise and decoherence, might be naturally built into the structure of space-time itself. The redundancy required for quantum error correction would ensure that local perturbations to the quantum state couldn't destroy the global geometry, providing a mechanism for maintaining the stability of emergent space-time. These developments have led to a new field called quantum gravity phenomenology, which seeks to identify observable consequences of quantum gravitational effects. Researchers look for signatures of space-time discreteness in gravitational wave detectors, search for violations of Lorentz invariance in cosmic ray observations, and study the polarization of light from distant galaxies for evidence of quantum gravitational birefringence. So far, no definitive evidence for quantum gravitational effects has been found. The energy scales where such effects become important remain far beyond the reach of current experiments, but the theoretical framework connecting entanglement, space-time, and gravity continues to evolve rapidly, suggesting new avenues for both theoretical exploration and experimental investigation. The possibility that gravity emerges from quantum entanglement represents one of the most profound conceptual shifts in physics since Einstein's original formulation of general relativity. If space-time really is woven from quantum correlations, then our entire understanding of space, time, and causality would need to be reconsidered. For our story about gravitational propagation speed, the emergence of space-time from entanglement suggests that the question might not have a simple answer. At the level of classical space-time, gravitational effects propagate at the speed of light, as confirmed by gravitational wave observations. But at the level of quantum entanglement that creates space-time, correlations can be instantaneous and non-local. The challenge is to understand how these two levels of description fit together, and whether the quantum substrate ever manifests itself in observable violations of Einstein's speed limit. The answer might depend on the specific details of how entanglement creates geometry, and under what circumstances the classical approximation breaks down. But what if, just hypothetically, gravity did ignore the speed of light? What would such a universe look like, and why don't we live in it? Let's step into an alternate universe for a moment. Imagine a cosmos where Einstein was wrong about gravitational propagation speed, where Newton's intuition about instantaneous action at a distance was correct. In this hypothetical reality, gravity ignores the cosmic speed limit entirely. When a massive star collapses into a black hole in the Andromeda Galaxy, Earth feels the change in gravitational field instantly, not after 2.5 million years when light from the event finally reaches us. At first glance, this might seem like a minor technical detail. After all, gravity is already the weakest of the fundamental forces. What difference would it make if gravitational effects propagated instantly rather than at the speed of light? The answer, as we'll discover, is that instantaneous gravity would create a universe so fundamentally different from our own that intelligent life might never have emerged to contemplate these questions. The most immediate consequence of instantaneous gravity would be the complete breakdown of causality as we understand it. In Einstein's relativity, the concept of simultaneity is relative. Events that appear simultaneous to one observer occur at different times for another observer, moving at a different velocity. This relativity of simultaneity means that faster-than-light signals can be used to construct causal paradoxes, where effects precede their causes. Consider a simple scenario involving two space stations moving past each other at high speed. If gravity could propagate instantaneously, an observer on the first station could use gravitational signals to communicate with the second station faster than light. Due to the relativity of simultaneity, the signal would arrive at the second station before it was sent from the first station, as measured by clocks on the second station. The second station could then reply immediately, sending its own instantaneous gravitational signal back to the first station. This reply would arrive at the first station before the original signal was sent, creating a closed causal loop where information travels backward in time. The operators of the first station could receive messages from their own future, learning about events before those events actually occur. Such causal violations would make rational decision-making impossible. If you could receive information from the future, you could learn about the consequences of your actions before taking them. You could then choose different actions to avoid negative consequences, preventing the future events that sent you the warning in the first place. The logical contradictions would multiply without limit. But the problems with instantaneous gravity extend far beyond philosophical puzzles about causality. The orbital mechanics of planetary systems would be completely different in a universe where gravitational effects propagate faster than light. The stability of orbits depends on a delicate balance between gravitational attraction and orbital velocity, and this balance would be disrupted if gravitational effects could outpace the motions of the objects creating them. To understand this, consider what happens when Earth moves in its orbit around the Sun. In our universe, Earth feels gravitational attraction toward the Sun's current position because the static gravitational field is already established throughout the solar system. But if gravitational effects had to propagate instantaneously to track the Sun's motion, the situation would be different. Earth travels about 30 kilometers per second in its orbit. If gravitational attraction always pointed toward the Sun's instantaneous position, it would create a constant torque that would either accelerate or decelerate Earth's orbital motion, depending on the detailed dynamics. Over millions of years, this would cause Earth's orbit to either spiral inward toward the Sun or expand outward, eventually ejecting our planet from the solar system entirely. Binary star systems would face even more severe problems. When two massive stars orbit each other at close range, they can reach orbital velocities of hundreds or even thousands of kilometers per second. If each star felt gravitational attraction toward its partner's instantaneous position, the resulting orbital dynamics would be chaotic and unstable. The stars would experience gravitational forces that constantly lead or lag their orbital motion, creating runaway instabilities that would quickly destroy the binary system. The stars might spiral into each other and merge, or they might be flung apart at high speeds. Either way, the long-lived stable binary systems that we observe throughout the galaxy could not exist. The problems become even more acute when we consider systems with multiple interacting objects. The gravitational three-body problem, involving the motion of three masses under their mutual gravitational attraction, is already chaotic and unpredictable in our universe, where gravity propagates at the speed of light. With instantaneous gravity, the chaos would be even more severe. Planetary systems with multiple planets would be fundamentally unstable. The instantaneous gravitational interactions between planets would create resonances and feedback effects that would quickly disrupt their orbits. Jupiter and Saturn, whose gravitational influence helps stabilize the orbits of the inner planets in our solar system, would instead destabilize those orbits through instantaneous gravitational perturbations. The formation of planetary systems would also be affected. Planets form through the gradual accumulation of dust and gas in disks around young stars. This process requires millions of years of stable orbital motion for small particles to slowly collide and stick together, building up larger and larger objects through countless gentle encounters. But with instantaneous gravity, the orbital dynamics of the protoplanetary disk would be chaotic from the beginning. Density fluctuations in the disk would create instantaneous gravitational disturbances that would prevent the orderly accumulation of material. Instead of forming planets, the disk material might either fall into the central star or be ejected from the system entirely. Even if planets somehow manage to form despite these difficulties, their long-term evolution would be problematic. The Earth-Moon system, for example, owes its stability to tidal effects that gradually transfer angular momentum from Earth's rotation to the Moon's orbit. These tidal effects depend on the finite time it takes for gravitational influences to propagate, creating the delay necessary for energy dissipation. With instantaneous gravity, tidal effects would work differently, potentially making the Earth-Moon system unstable over geological timescales. The Moon might either spiral into Earth or escape to interplanetary space, depriving our planet of the tidal forces that may have been crucial for the development of life in tidal pools and coastal environments. The effects of instantaneous gravity would extend beyond individual planetary systems to the large-scale structure of the universe itself. Galaxies are held together by the gravitational attraction of their constituent stars, gas clouds, and dark matter. The spiral arms of galaxies like the Milky Way are maintained by density waves that propagate through the galactic disk at specific speeds related to the orbital velocities of stars. If gravity propagated instantaneously, these density waves would behave very differently. The gravitational disturbances that create and maintain spiral structure would propagate much faster than the orbital motion of stars, potentially disrupting the delicate balance that maintains galactic structure. Spiral galaxies might not be able to maintain their characteristic shape, instead evolving into amorphous blobs of stars with no organized structure. Galaxy clusters, the largest gravitationally bound structures in the universe, would also be affected. These clusters contain hundreds or thousands of individual galaxies, held together by their mutual gravitational attraction. The dynamics of galaxy clusters are already complex, with galaxies following complicated orbits through the cluster's gravitational potential. With instantaneous gravity, the orbital dynamics within galaxy clusters would become even more chaotic. Galaxies would experience sudden gravitational impulses from distant cluster members, leading to high-velocity encounters that could disrupt individual galaxies or eject them from the cluster entirely. The stable, long-lived galaxy clusters that we observe might not be able to form or persist. Perhaps most fundamentally, instantaneous gravity would create problems for our understanding of energy and momentum conservation. In our universe, gravitational waves carry energy and momentum away from their sources, providing a mechanism for binary systems to lose energy and spiral together. This energy loss is crucial for understanding phenomena like the orbital decay of binary pulsars and the eventual merger of black hole and neutron-star pairs. Without gravitational wave radiation, binary systems would have no mechanism for losing energy and angular momentum. Closed binary stars would remain in stable orbits indefinitely, never spiraling together to create the spectacular mergers that we observe as gravitational wave sources. The neutron-star merger that provided such precise measurements of gravitational wave propagation speed would never have occurred. The absence of gravitational wave radiation would also affect the early universe. During cosmic inflation, quantum fluctuations in the gravitational field were stretched to macroscopic scales, creating the primordial gravitational waves that may have left observable imprints in the cosmic microwave background. Without gravitational waves propagating at the speed of light, this mechanism for creating primordial gravitational wave signatures would not exist. Even black holes would behave differently in a universe with instantaneous gravity. The event horizon of a black hole is defined as the surface beyond which nothing, not even light, can escape. But this definition depends on the assumption that gravitational effects propagate at the speed of light. If gravity were instantaneous, the concept of an event horizon might not make sense. Information that falls into a black hole would be able to influence the external gravitational field instantaneously, potentially allowing that information to escape faster than light. This would resolve the black hole information paradox, but at the cost of creating new paradoxes related to causality and the nature of space and time near black holes. The thermodynamic properties of black holes would also be affected. Hawking radiation, the quantum mechanical process by which black holes slowly evaporate, depends on the relationship between the black hole's event horizon and the propagation of quantum field fluctuations. With instantaneous gravity, the calculation of Hawking radiation would need to be completely reconsidered. On smaller scales, instantaneous gravity would affect the behavior of matter in extreme gravitational fields. Neutron stars, the ultra-dense remnants of stellar explosions, are held together by the balance between gravitational attraction and the quantum pressure of degenerate neutron matter. If gravitational effects propagated instantaneously, this balance might be disrupted, potentially making neutron stars unstable or preventing their formation entirely. The detection of gravitational waves, which has opened a new window on the universe, would be impossible in a cosmos with instantaneous gravity. LIGO and other gravitational wave detectors work by measuring the tiny stretching and compression of space as gravitational waves pass through them. But instantaneous gravitational effects would not create propagating waves, instead producing sudden, discontinuous changes in the gravitational field. This would eliminate one of our most powerful tools for studying black holes, neutron stars, and other exotic objects. The rich phenomenology of gravitational wave astronomy, from the chirp signals of merging black holes to the complex waveforms of neutron-star collisions, would simply not exist. Perhaps most importantly for the development of life, instantaneous gravity would make the universe a much more violent and unpredictable place. The stable, long-lived stellar and planetary systems that provide the conditions necessary for biological evolution would be much rarer or might not exist at all. Complex organisms require billions of years of stable environmental conditions to evolve, but instantaneous gravity would make such stability extremely difficult to achieve. The Earth itself might never have developed the conditions necessary for life. Our planet's stable orbit, protective magnetic field, and long-term climate stability all depend on gravitational interactions that unfold over millions or billions of years. The sudden, instantaneous gravitational disturbances that would occur in an instant gravity universe might prevent these favorable conditions from ever developing. Even if life somehow managed to emerge despite these challenges, its evolution would be constantly threatened by gravitational catastrophes. Sudden changes in planetary orbits, stellar encounters, or galactic dynamics could wipe out complex ecosystems before they had time to adapt. The long, gradual evolutionary processes that produce the diversity of life on Earth might be repeatedly interrupted by gravitational chaos. The universe we actually inhabit, with gravity propagating at exactly the speed of light, seems to be precisely tuned to allow for the stable, predictable conditions that make complex structures possible. From the formation of galaxies and stars, to the evolution of planetary systems and the development of life, everything depends on the careful balance between gravitational attraction and orbital motion that Einstein's theory provides. This brings us to our final question. If instantaneous gravity would create such a chaotic and inhospitable universe, why do we find ourselves in a cosmos where gravity respects the speed limit? Is this just a fortunate coincidence, or does some deeper principle ensure that gravity must propagate at the speed of light? We've traveled through 3 centuries of gravitational theory, from Newton's instant action at a distance to Einstein's curved space-time, from quantum foam to cosmic catastrophes. We've explored every possible loophole, every theoretical escape route, every exotic scenario that might allow gravity to break the cosmic speed limit. And at the end of this journey, we arrive at a conclusion that is both elegant and profound. Gravity respects the speed of light not because it has to, but because the universe would be uninhabitable if it didn't. The evidence is overwhelming and comes from every direction. LIGO's detection of gravitational waves racing across the cosmos at exactly the speed of light, the precise timing of GW 170817, where gravitational waves and gamma rays arrived within seconds of each other after traveling for 130 million years. The stable orbits of planets and binary stars that would be impossible if gravitational effects propagated at any other speed. But perhaps the most compelling evidence comes from the simple fact that we exist at all. In a universe where gravity ignored the speed limit, the delicate cosmic choreography that allows complex structures to form and persist would be impossible. Stars would not burn steadily for billions of years, planets would not maintain stable orbits, galaxies would not hold together long enough for heavy elements to be forged in stellar cores and dispersed through space. The speed of light is not just a number that physicists happen to have measured. It represents something far more fundamental, the maximum rate at which cause and effect can propagate through the universe. This speed limit is built into the very fabric of space-time itself, emerging from the mathematical structure that Einstein discovered when he realized that space and time are unified into a single dynamic entity. In Einstein's theory, the speed of light appears not because light is special, but because space-time has a fundamental structure that defines a maximum propagation speed for any causal influence. Massless particles like photons travel at this maximum speed because they have no choice. They must follow null geodesics through space-time, paths that connect events that can influence each other with no delay. Gravitational waves, being ripples in space-time itself, also follow these null geodesics. They propagate at the speed of light not because they're somehow similar to light waves, but because they're disturbances in the same space-time fabric that defines the causal structure of the universe. When LIGO detects gravitational waves arriving at light speed, it's really measuring the fundamental geometry of space-time. This geometric interpretation helps us understand why gravity appears to act instantaneously in some situations, while clearly propagating at finite speed in others. The static gravitational field around a massive object, like the sun, doesn't propagate at all, because it's not going anywhere. It's simply the shape of space-time in the presence of mass, established when the mass first appeared, and persisting as long as the mass remains relatively unchanged. Planets orbiting the sun follow geodesics through this curved space-time geometry. They don't wait for gravitational signals because they're not responding to signals. They're responding to the local curvature of space-time right where they are. It's like a marble rolling in a bowl, following the shape of the bowl, without needing any communication from the mass that created the bowl's curvature. But when masses accelerate rapidly, they create dynamic changes in space-time curvature that must propagate outward as gravitational waves. These waves carry energy and information at exactly the speed of light, updating the global geometry of space-time as they spread. The waves don't violate causality because they're not signals in the usual sense, they're changes in the causal structure itself. This subtle distinction between static geometry and propagating waves resolves the apparent paradox that has puzzled physicists for over a century. Gravity doesn't act instantaneously, but it also doesn't need to send signals across space. Instead, it manifests as the geometry of space-time, which has both static and dynamic aspects that respect the fundamental causal structure of the universe. The mathematical elegance of this solution reflects something deeper about the nature of physical law. Einstein's field equations are not just descriptions of how gravity works. They're statements about the consistency of space-time itself. The equations ensure that the geometry remains mathematically coherent, with no contradictions or paradoxes that would make the universe logically inconsistent. This consistency requirement is so strict that it essentially forces gravity to propagate at the speed of light. Any other propagation speed would create inconsistencies in the field equations, leading to mathematical contradictions that would make the theory logically incoherent. The speed of light emerges not as an arbitrary constant, but as the unique value that makes space-time geometry self-consistent. The quantum mechanical aspects of gravity, while still poorly understood, seem to reinforce this conclusion. Quantum field theory requires that all interactions respect the causal structure of space-time, preventing faster-than-light signaling, even when quantum entanglement creates instantaneous correlations between distant particles. The quantum vacuum itself has a structure that preserves causality, even in the presence of virtual particles and quantum fluctuations. When physicists attempt to construct theories of quantum gravity, they find that preserving causality places severe constraints on the possible form of the theory. String theory, loop quantum gravity, and other approaches all struggle to maintain mathematical consistency while respecting the speed of light limit. The few theories that allow for faster-than-light effects typically suffer from instabilities or paradoxes that make them unphysical. This suggests that the speed of light limit is not just a feature of our particular universe, but a fundamental requirement for any self-consistent physical theory. The mathematical structures that describe reality seem to demand a finite maximum speed for causal propagation. Universes that violate this principle might simply be mathematically impossible. But the story becomes even more remarkable when we consider the precise value of the speed of light itself. The number 299,792,458 meters per second seems arbitrary, but it's intimately connected to the fundamental constants that determine the properties of atoms, molecules, and all the complex structures they can form. If the speed of light were significantly different, the balance between electromagnetic and gravitational forces that allows atoms to exist would be disrupted. Stars would burn too quickly or too slowly to support the long-term stability needed for planetary systems. The rate of cosmic expansion would be altered, potentially preventing galaxies from forming or causing the universe to collapse before complex structures could develop. The anthropic principle suggests that we observe the speed of light to have precisely the value it does, because only universes with this value can support the development of observers like ourselves. The speed limit is not just mathematically necessary for consistency, but also precisely tuned to allow for the emergence of complexity and life. This fine-tuning extends to the gravitational constant itself, which determines the strength of gravitational effects relative to other forces. If gravity were much stronger, stars would burn out quickly, and black holes would dominate the universe. If gravity were much weaker, matter would never collapse to form stars and galaxies. The observed value seems to be precisely calibrated to allow for the rich cosmic ecology we observe. The relationship between gravity and the speed of light also illuminates deep connections between geometry, causality, and information. Einstein's theory shows us that space-time is not just a passive stage on which physical events unfold, but an active participant that shapes the flow of cause and effect. The geometry of space-time determines which events can influence which other events, and at what rate information can propagate between them. This geometric view of causality has profound implications for our understanding of time itself. In Newton's universe, time was absolute and universal, flowing at the same rate for all observers. But Einstein showed us that time is relative, flowing at different rates in different gravitational fields, and for observers moving at different velocities. The speed of light serves as a universal conversion factor between space and time, allowing us to measure both in the same units and understand their fundamental unity. When we say that gravitational waves propagate at the speed of light, we're really saying that they propagate along the light cones that define the causal structure of space-time. These light cones represent the boundaries of possible influence. Events inside your past light cone can affect you. Events inside your future light cone can be affected by you. Events outside your light cone are causally disconnected from you, at least until light or gravitational waves have time to travel between you. This causal structure is what prevents the paradoxes and inconsistencies that would arise from faster than light propagation. The discovery of gravitational waves has opened new windows on this causal structure, allowing us to observe the propagation of space-time disturbances in real time. Each gravitational wave detection is a direct measurement of the light cone structure of space-time, confirming that the universe really does respect the causal boundaries that Einstein's theory predicts. But perhaps the most profound lesson from our journey through gravitational theory is that the apparent limitations of nature often reflect deeper necessities. The speed of light seems like an arbitrary barrier that prevents us from traveling to distant stars or communicating across the galaxy instantaneously. But this barrier is actually what makes the universe stable enough for stars, planets, and life to exist in the first place. Similarly, the weakness of gravity, which makes it so difficult to detect gravitational waves or test theories of quantum gravity, is actually essential for the existence of complex structures. If gravity were as strong as the electromagnetic force, atoms would collapse into black holes, and chemistry would be impossible. The weakness of gravity is not a design flaw, but a feature that makes complexity possible. The universe reveals itself to be a delicately balanced system, where every fundamental constant and physical law contributes to the overall stability and consistency of the whole. Gravity's respect for the speed limit is not an arbitrary constraint, but an essential component of this cosmic balance. It ensures that cause and effect flow in rational directions, that stable structures can persist for billions of years, and that information and energy can propagate in predictable ways. As we push the boundaries of gravitational physics with ever more sensitive detectors and sophisticated theories, we continue to find confirmation of Einstein's century-old insights. The universe operates according to principles that are both mathematically elegant and physically necessary. The speed of light limit is not just a rule that gravity happens to follow, but a fundamental aspect of the logical structure that makes reality possible. Looking toward the future, gravitational wave astronomy will continue to test these principles with increasing precision. Future detectors will measure gravitational wave propagation speeds to even higher accuracy, search for subtle deviations from Einstein's predictions, and probe the quantum nature of space-time itself. Each new detection will provide another opportunity to verify that gravity really does respect the cosmic speed limit, But based on everything we've learned, the outcome seems certain. Gravity will continue to obey Einstein's equations. Gravitational waves will continue to propagate at exactly the speed of light, and the universe will continue to operate according to the rational causal structure that makes complexity and consciousness possible. The journey from Newton's instant gravity to Einstein's light-speed waves represents one of the greatest intellectual adventures in human history. It has taken us from simple mechanical models to the deepest questions about space, time, and existence itself. And at the end of this journey, we find that gravity doesn't ignore the speed of light. It obeys it perfectly, just in a way that feels invisible. It doesn't rush because it doesn't need to. It's not a message racing across space. It's the shape of the message itself. We began this journey with a simple question. What if gravity ignores the speed of light completely? What if it could reach across the cosmos instantly, connecting stars, galaxies, even minds, in ways we can't yet explain? Now, after traveling through 3 centuries of physics, quantum mysteries, and cosmic catastrophes, we have our answer. Gravity doesn't ignore the speed of light. It obeys it perfectly, just in a way that feels invisible. It doesn't rush because it doesn't need to. It's not a message racing through space, desperately trying to keep up with the cosmic speed limit. It's the shape of the message itself. When Isaac Newton first imagined gravity as an instantaneous force reaching across infinite distances, he was grappling with one of the deepest mysteries in physics. How can one object influence another across empty space without anything connecting them? His mathematical answer was brilliant and lasting, but his intuition about instantaneous action would eventually prove to be beautifully wrong. Einstein showed us that gravity isn't a force at all, but the curvature of space-time itself. This geometric insight transformed our understanding from mysterious action at a distance to elegant mathematical necessity. Massive objects don't reach out and grab other objects across space. Instead, they curve the fabric of reality itself, and other objects simply follow the straightest possible paths through that curved geometry. This curvature doesn't propagate because it doesn't need to propagate. It's already there, woven into the structure of space-time itself. When Earth orbits the Sun, it's not waiting for gravitational signals to arrive from our star. It's following a geodesic through curved space-time, like a river following the contours of a valley that was carved millions of years ago. But when that curvature changes rapidly, when black holes spiral together or neutron stars collide, then something does propagate. Gravitational waves ripple outward at exactly the speed of light, carrying news of cosmic violence across the universe. These waves are not gravity itself, but changes in gravity, disturbances in the eternal geometry that defines the shape of space and time. The precision with which these waves respect Einstein's speed limit is breathtaking. After racing across 130 million years of space, gravitational waves from colliding neutron stars arrived at Earth within seconds of the light from the same event. This represents a timing accuracy better than 1 part in 100 billion, confirming Einstein's prediction with almost unimaginable precision. This exquisite obedience to the cosmic speed limit isn't accidental. It's essential for the existence of everything we know and love. In a universe where gravity could travel faster than light, the stable orbits that allow planets to exist would be impossible. The long, burning stars that forge heavy elements would be chaotic and short-lived. The galaxy clusters that provide the cosmic architecture for structure formation would fly apart in gravitational chaos. Most profoundly, the rational flow of cause and effect that makes logic and science possible would break down entirely. Faster than light gravity would allow effects to precede their causes, information to travel backward in time, and contradictions to infect the very foundations of reality. The universe would become a place where rational thought itself would be impossible. The speed of light is not just a number that physicists happen to have measured. It represents the fundamental rate at which reality processes information, the maximum speed at which one event can influence another. This speed limit is built into the mathematical structure of space-time itself, emerging from the geometric relationships that Einstein discovered when he unified space and time into a single dynamic entity. Gravity respects this limit not because it's similar to light, but because it's made of the same stuff as light's highway. Gravitational waves and light waves both travel through space-time. Both follow the null geodesics that define the causal structure of the universe. Both carry information at the maximum rate that reality allows. But gravity has a secret that light doesn't share. While light must always travel at the cosmic speed limit, gravity can also manifest as static curvature that doesn't travel at all. This dual nature gives gravity its mysterious character, allowing it to seem both instant and finite, both immediate and delayed, depending on the situation. The static gravitational field that holds Earth in orbit around the Sun was established 4.5 billion years ago, when the solar system first formed. It doesn't need to be refreshed or updated because it's not a signal, it's a shape. The dynamic gravitational waves that LIGO detects are ripples in this shape, carrying information about distant events at the speed of light. This geometric view of gravity reveals something profound about the nature of physical law. The universe operates according to principles that are both mathematically elegant and physically necessary. Every fundamental constant, every force, every speed limit contributes to the delicate balance that makes complexity and consciousness possible. If gravity propagated at any speed other than the speed of light, this balance would be disrupted. The mathematical consistency of Einstein's field equations would be violated. The causal structure of space-time would become contradictory. The universe itself would become logically impossible. The anthropic principle suggests that we observe gravity to respect the speed limit precisely because only universes with this property can support the development of observers like ourselves. We don't live in a cosmos with instant gravity, because such a cosmos couldn't sustain the stable structures needed for life and intelligence to emerge. But there's something even deeper here. The speed of light limit doesn't just make our universe habitable, it makes our universe comprehensible. The rational causal structure that Einstein's theory preserves is what allows science itself to work. If effects could precede causes, if information could travel backward in time, then the logical foundations of knowledge would crumble. The fact that gravity obeys the same causal rules as everything else means that the universe is ultimately knowable. We can trace chains of cause and effect, make predictions about future events, and understand the connections between distant phenomena. The cosmic speed limit is what makes the cosmos a place where minds can arise and contemplate their own existence. Quantum mechanics adds subtle layers to this story, revealing that the universe has non-local correlations that transcend classical notions of space and separation. Entangled particles remain connected across arbitrary distances, sharing quantum information faster than light could travel between them. But these quantum connections can't be used to send controllable signals, preserving the causal structure that makes rational thought possible. Some theories suggest that space-time itself emerges from quantum entanglement, that the geometry we observe at large scales reflects patterns of quantum correlation at microscopic scales. If true, this would mean that gravity's geometric nature has quantum roots, that the curvature of space-time is really a manifestation of the network of quantum connections that weaves reality together. But even in these exotic theories, the classical causal structure remains intact. Space-time may emerge from quantum correlations, but the emergent geometry still respects Einstein's speed limit. The quantum substrate may allow for instantaneous correlations, but these correlations remain hidden from observers who can only access the classical geometry that emerges at large scales. The search for quantum gravity continues to push the boundaries of human understanding, revealing connections between geometry, information, and causality that Einstein never imagined. But every new discovery seems to reinforce the fundamental insight that reality has a rational structure, that causes precede effects, and that information propagates at finite speeds. As we look toward the future, gravitational wave astronomy will continue to test these principles with ever greater precision. New detectors will probe the quantum nature of space-time itself, search for signatures of extra dimensions, and explore the most extreme gravitational environments in the universe. Each new detection will provide another opportunity to verify that gravity really does respect the cosmic speed limit. The story of gravity's speed is ultimately a story about the nature of reality itself. It's about the mathematical structures that make the universe consistent, the physical principles that make complexity possible, and the causal relationships that make knowledge achievable. Gravity doesn't ignore the speed of light because the universe would be impossible if it did. In the end, the question we started with contained its own answer. We asked what if gravity could ignore the speed of light completely, as if this would be a remarkable exception to the rules of physics. But now we understand that gravity's obedience to the speed limit isn't an exception, it's the foundation. It's not a constraint that limits gravity's power, but the principle that makes gravity's power consistent with the existence of everything else. The universe is a place where gravity knows no hurry because it doesn't need to hurry. It shapes space and time themselves, defining the stage on which all other phenomena play out. It doesn't race across the cosmos carrying messages because it is the medium through which all messages must travel. This is the deepest lesson of our journey through gravitational physics. The apparent limitations of nature often reflect deeper necessities. The speed of light seems like a barrier that constrains what's possible, but it's actually the principle that makes anything possible at all. The weakness of gravity seems like a design flaw that makes it hard to study, but it's actually the feature that allows atoms, stars, and galaxies to exist. The universe reveals itself to be not a collection of arbitrary rules and constants, but a unified whole where every part contributes to the stability and comprehensibility of the entire system. Gravity's respect for the speed limit is not just one more law of physics, but a fundamental aspect of the rational structure that makes reality itself possible. And so we return to where we began, with a sense of wonder at the elegant simplicity that underlies the apparent complexity of the cosmos. Gravity doesn't ignore the speed of light. It embodies it, embraces it, and depends on it. It doesn't need to move faster than light, because it doesn't need to move at all. It simply is, woven into the very fabric of existence, patient and eternal, and perfectly content to let the universe unfold at exactly the pace that makes sense, beauty, and consciousness possible.